Hey guys, welcome once more to my YouTube channel. Today, as you can see on your screen, we are going to be talking about nomenclature of organic compounds, naming basic organic compounds. Now, we'll start by naming the simple alkanes, then we'll move on to more complex alkanes. All right. Now, there are two, structures, basic, structures of an organic compound. You have the aliphatic, which is the straight chain, or you have the cyclic, which has which is rounded. All right. So you see all this as we move through the video. Now I want to show you the basic forms of representing organic compounds, structures of organic compounds. All right. These are the three forms. This one is known as the Bode-line formula or Lewis structure. This is how Lewis structure basically, if you did your basic chemistry, this is the Bode-line formula. You have the condensed formula, where basically there's no lines but they are condensed, you understand, having the methyl group, the methylene, and the rest of that. And of course, the most popular and the one people denote as crazy line drawing. Yeah, that's this one. Line drawing is simply just using lines to represent these structures. So we'll get into the details as we move forward. Now, in naming of organic compounds, we have to know the basic prefixes. All right. So right here on your screen, you have the basic prefixes for naming any organic compounds. You have to hold this one in your off head. All right. It's pretty easy. If you did your math, this would also be easy for you. Apart from the meth, heads, prop, I think the pent, hex, hept, those ones are much easier to recognize and learn. Now, meth at this point, it simply means carbon compounds that only have one carbon atom in their chain. All right, that's what meth means. And so the rest of them: earth is 2, prop is 3, boot is 4, pent is 5, hex is 6, hept is 7, 8 is oct, non is 9, and 10 is dec. So there are many other more, but I would like to just use these basic ones. Of course, they will be going a long way to help us in this organic chemistry course. So, but essentially these are just the basic prefixes. Okay, now I actually did not prepare the slide for the surfaces, but as functional groups, anyway, we'll get to that part. As functional groups, some ends with ane, that is ane. You have ends with ine. Ane is basically when every bond is single. All right. Ine is when the bond is 3. All right. Then in is when there is a double bond, is double bonded. All right. In single bond, ine triple bond, in double bond. These are suffixes. Now also, when they act as functional groups, you understand, as functional groups, they also end with the suffix "-ile". We have methyl, ethyl. As we move forward, you probably see what I'm trying to introduce here. Now, we'll first of all start by naming continuous chains. All right, chains that does not branch. Of course, in aliphatic compounds, we do have branching. Not all of them goes in a straightforward manner. At some point, some branches, forming what we know as isomers, forming this phenomenon known as isomerism, where compounds, they have the same molecular number but different structural formula. You get. So now let's start from the basic name. Of course, everyone knows this one. It's popular. We use it as our cooking gas. All right, basically an odorless colorless gas, with very, very, very low boiling points. All right, that's why it easily explodes in the mind. Of course, this compound I'm talking about that has one single bond. Okay, can you guys guess the prefix that follows this organic compound? Of course, you guessed it right. It's meth. So meth works. Remember what I told you about having just single bonds. There's no double bond in this structure. So what do you think will be the suffix? Of course, you guessed it right. Ane. So this is basic methane, right? And carbon has completed this octet structure because carbon is needs to bond to 4 other atoms in order to complete its octet structure. Now we'll move to the second one. I'm trying to make it easier. Let's go step by step. Let's not rush things. Let's go step by step. Now we have the two the compound containing 2 carbon atoms here. Like I said, you remember this 2. So what does 2 mean? Earth. Does it have any single any double bond? No. So it's what? Ethane. So this is ethane. All right, ethane. Now let's move on to the I want you to guess this before we try it out. Okay, you probably guessed it right. This is prop because of the 3 carbon atoms, and ane because there is no single bond. Now what if there is a single bond somewhere here? All right, of course carbon atom will have more than 4 bonded atoms to it, so we have to remove this H. Let's assume this H is out. Of course, this makes it more logical and complete, rational for carbon. Now at this stage we will no longer have this ane again, rather we have the ane, propane. But we're not talking about alkanes here, so let's just continue with the alkanes. I'm not talking about alkanes, so we'll move on to the next. Of course, I wanted to show you this compressed form, how it really works, though we moved way too forward here, but I needed a structure that can show you the compressed form, how it works. Now basically all you need to do, as you have seen this structure, is to count the carbon atoms. All right, before we get to the line notation, this is important. I show you first this one. So how many carbon atoms are here? You have 1, 2, 3, 4, 5, 6, 7, 8. So what do you think the root name of this would be? Let's refresh our minds. So what should it be? Oct. Now of course you don't see much lines here, so you can't really tell whether there is a double bond, but there's an easy way to do it. When you see that all these the ends are made up of the ends here are bonded to 3 hydrogen, and every other one is bonded to 2, you definitely know that this is an alkane and not an alkane or an alkyne. So basically this is an octane. You see, very simple, easy, compressed form. Now let's move forward. Line, the hideous line. Did I say hideous? It's quite pretty, but people usually confuse it as very hard. I think this is the easiest way to denote or represent organic compounds. It's very easy, quite simple. Now you might ask, how do we actually know how to start counting? Where is the carbon atom located? It's quite easy. At any junction and terminal, you have a carbon atom. Terminal, I mean, is here. This is a terminal. This is a terminal. It has a carbon atom. All right, with 3 hydrogen. So basically, you get, now here is 2. Every junction you have carbon atom here. Now if you have to count the carbon atoms in this molecule, how many will it be? All right, let's start from the first terminal, the proximal terminal. 1, 2, 3, 4, 5, 6, 7, and of course anything 7 prefix is hept, and there's no double bond. As you can see, if there's a double bond, there will be a line like this somewhere in here, or somewhere anywhere. Just there will be a double bond, you will see a double line, but in this case there is no double line. So yeah, it's just a single, it's a straight, it doesn't have any single bonded, all of them. So this is basically a heptane. All right, it's easy. We have to name a lot. Now, let me just draw another type. Let me know if you can do it. We have to make sure we land firmly in the basics, so before we get to the complex structure, it will be very easy for us to go. So try naming this compound. I'll give you some time to think on it. Okay, as you would have guessed already, the terminals, you count the terminals, 1, then count the junction again, the proximal terminal, count the junctions, 1, 2, 3, 4, 5, and 5 is what? It's a pent, so it's what we say, pentane. Of course, I know you guessed it right. All right, let me give a tricky one here to see if you can be able to, deal with it. Let's test our logic here. Sorry about that. I think that's too early. All right, can you name this? Of course you can, trust you. Now we have 1, 2, 3, 4, 5, 6. All right, we could easily go. You can simply say, of course, we know, we have established it has 6 carbon atoms, giving it the prefix hex. But now we are seeing something weird somewhere here. Can you see what I'm seeing? There's a double bond here, and we can't just go ahead and call it hexane while we are seeing something different. It's not like the normal hexane we know. So with a double bond is a hexane, 1 hexane, but let's just ignore the 1, but it's a hexane. Now moving forward. All right, let's go to the branched compounds. So basically, branch compounds, these are compounds that are not really continuous. You have they don't have a continuous chain. You might have a compound that goes straight like this, and at some point here it branches. It can branch at any point. It can branch to have a functional group. So we're going to treat this one specially, of course, because most of organic compounds, which are popular, they are mostly branched. You hardly find a straight line. But let's get to it. Of course, this is our first guy. Very simple, very easy. All right. So before I solve this, I would like to show you the the simple structure, the bold line structure, the Lewis structure of it, how it looks. You can see that it's really simple. You just like the line notation might look like it's not, but it's very easy. Now, first of all, let me just draw it for you guys to see here. C H H H C C C. So this is the spread out form of this compound here. As you can see, all the terminals and junction are well represented. all the C's are in the right place. Now let's take a critical look on how we are going to identify this compound with all its branches. So rule number one in identifying or naming these compounds that are branched is, first of all, you have to take the side with the longest continuous chain. Like, for example, it could be this. Okay, now let's take side. Let's just I'll show you the different chains here. You can have from here to here. That is one chain there. You can have straightforward like this. Okay, that's another chain there. Or you can have from here to here. You see, there are three basic paths to follow in this compound, but we're actually going to pick the one with the longest carbon atoms, the one that has the most carbon atoms. So we simply choose that by counting. In this red chain, red line, we have how many? We have one, we have two, we have three, we have four. Okay, in root 1 we have only 4. All right, so in root 2, how many do we have? 1, 2, 3, 4, 5. We have 5 in root blue, or root yellow, sorry. Then in root blue, how many do we have? 1, 2, 3, 4, 5. Well, I'm just drawing this out for you. We're not going to be writing it out like this any longer. After this parts, we are going to be using the line to represent it. It's much easier with lines. So we can see that 2 roots here have 5 carbon atoms in their chain. So which one are we going to pick? Well, of course, the answer is any one. Then you can pick any one. They'll basically give you the same the same name, of course. So now, as you have established the one with the longest, and let's just take the straight one, of course, the yellow one, of course. So we start by numbering it, giving these functional groups. These are functional groups. These branches here. This is a methyl functional group. Generally, they are known as alkyls. So, but since this one has 1 carbon atom, like I said before, it is known as a methyl. We call it a methyl functional group. Is a substitute. So we are going to number these carbon atoms, making sure that the number the carbon that bears this functional group has the lowest possible number. You get, they have the lowest possible number. We see situations where we can see that some of them will not have the lowest possible number, and we have to choose between the one that has the lowest possible number and the other. So at this point, we start counting from here, not here. Let's see, for example, if you count from here, 1, 2, 3, 4, 5. Okay, now we have that carbon 3 has a methyl group. We have that carbon 4 has a methyl group. Okay, that is naming it like that would be wrong in IUPAC system of nomenclature. So we rather start from start from the other end to count. You have 1, 2, 3, 4, 5, and now they have the lowest possible number. Initially it was 3 to 4, but now it's 2 to 1. In fact, when you sum up the both, you actually know which path to go through. You sum up the both. Like the sum of this one is 3 plus 2 is 5, while the other one is 3 plus 4 is 7. You pick the one with the lowest sum now, which is so. Now we are through with we are through with figuring out the compound the numbers of the the number of the carbon number of which the functional group is attached. Is 1, 2, 3. So this is easy. We start by naming, stating the number on which this I should have really started the one without the prefixes such as die, try, but I'll still name it though. We'll get to that parts. Of course, I know you are smart enough to do the initials. So we start by counting the numbers first, since they are the same functional group present, the methyl functional group. So you have 2, 3, your hyphen, very important, dimethyl, and of course we counted 5 carbon atoms to be the longest chain. So these 2, 3 represents the carbon atom which the methyl group functional group are present. Di means that actually 2 methyl functional group present. So 2 dimethyl pentane. You don't need a hyphen here. Pentane. Why in? Because there's no double bond there present. So this is 2 dimethyl pentane. Pretty straightforward, easy to go. Alright, like I said, I should have really started with the very simple one. So I'm going to draw a simple structure for you to name. Let's see if you can get it right. Alright, I'm attaching the functional group at this point, the methyl functional group. Alright, so again we start by picking the long chain. At this point it is pretty obvious which chain is the longest here. You can't say it's this one because, as you can see, it's quite apparent. It's quite obvious. So we start by counting the longest chain, the parent chain, which is 1, 2, 3, 4, 5, 6, 7, hept. Then we keep it aside to be at the end of the whole naming. So now let's identify the carbon atom with the functional group methyl. Alright, counting from both sides, you will actually see that it will all end in 4, 4. I actually made it equal so that there won't be any confusion of which side to start counting with. So if you count from this side, 1, 2, 3, 4, it's at 4. Count from this side, 1, 2, 3, 4. It's also at 4. So basically this one is very simple. 4, no dimethyl is not 2, so it's single. So dimethyl, 4 methyl, methyl Y, 4 methyl heptane. Pretty easy. Alright, let's move deeper again. Alright, this is our guy here. Alright, so guys, first of all, as usual, identify the longest chain, the longest pathway. Of course, you can see here that there are 3 pathways here. The long one here, the other that goes like this, the one that goes like this, finally the one that goes like this. So we identify the one with the longest chain. All right, so count 1, 2, 3, 4, 5, 6, 7, 8. 8. This one seems to be 8. 1, 2, 3, 4, 5, 6, 7. Of course, no need. 8 is is the longest chain here, so it should have the suffix octane, but it can't be just octane. So as usual, we start we need to identify the carbon atoms that bears the functional group. So we start by counting. Of course, this octane, we start with the one that is closest, that the carbon atoms are closest. All right, so let's say 1, 2, 3, 4, 5, 6, 7, 8. So let me just show you the the parts that might confuse you. Right now we have established, let's write down the numbers of this first initial carbon atoms. We have a group at carbon 3, we have a group at carbon 4, we also have a group at carbon 6. Now at the end we will sum it up to see what I'm saying. So let's start counting from the other side. We have 1, 2, 3, 4, 5, 6, 7, 8. So this time around we have the groups at carbon 3 as usual, but it comes to this part, it's no longer 4, it's 5. Then finally also at 6. So which parts are we taking? Of course, this part, we are taking the part with the least number. If you sum this up, it will give you around 13, while this would be 14. So we pick the one with the lowest number, which is this path, going through this path. All right, so what will be the name of our compound now? Very easy, it's 3, 4, 6 trimethyl, because of what? 3 methyl groups, 1, 2, 3. Trimethyl octane. Remember, no space between the methyl and octane, just because the screen is not long enough. They're all continuous, no space between them. So let's move to the next one. All right, it's getting more complicated, more and more. All right, how do you name this? Simply identify the chain, the longest chain, the longest continuous chain, and you can have 1, 2, sorry about that, 1, 2, 3, 4. You can have it either ways, any one you pick, it's okay. So we see at this point that we don't know which one to pick again. 1, 2, 3, 4, 1, 2, 3. So of course we pick the one with the shortest number, which is this side. This is 2, and this is 3. If you come from this side, this will be 2, this will be 3. All right, the question now is, they look the same, they are the same, but which one? If you sum both of them, they will equally give you 5, but which one should we pick? All right, we will pick the one with much functional group on this carbon atom, which is these 2. So we start with these 2. We're not going to say you're not going to say 3, 3, rather we say 2, 2, but let's get there. So this is going to be, of course we've counted it before, 1, 2, 3, 4, which is a butane. Butane will be the root name, butane. Now what is it going to be? 2, 2, 2,2,3 trimethyl butane. So that is the easy name for that. Remember, hyphen 2,2-trimethyl butane. This is the name of this compound. So we move on to the next. Okay, it's getting more complex as we go. So now we're not dealing with this usual functional group, the methyl again. As you can see, there's a new guy present. This functional group seems to be longer, right? It is longer, it doesn't seem to be longer. And this we name this prefix because of the 2 carbon atoms. We call it ethyl. So it's an ethyl, it's no longer methyl as usual. So how do we name this? Longest continuous chain as usual, which is carbon 1, 2, 3, 4, 5, 6. So it's going to have a root hexane. As you can see, all this is just an alkane. They are all alkanes. You haven't seen any double bonds, just branches. So that is the complexity here. So this is a hexane, of course. So where should we start numbering? You should get used to this. Of course, immediately I see it, I know I should start from this side. It can't be this side because it will definitely give this one a higher number when you go from this side. So we start from this side, it will get a more lower number. So let's not waste much time and just get to it. Is 1, 2, 3, 4, 5, 6, a hexane. So how do we start? Now this is where the the letters, the letters comes in. The formation, the arrangement of letters, where letters are considered. Let me make it more clear, like A, B, C, D, E. This is where order of arrangement of letters come in. Alright, because this one is an ethyl functional group, you actually have to acknowledge it first in the naming before you get to the methyl, because it's an M. In the English alphabet, the E comes before the M. So we have to acknowledge this guy first before getting to the methyl. So what do I mean by this? Now I'm going to name it this way. Watch out for the name. Watch what the name would be. It's now going to be 3-ethyl. Alright, 3-ethyl. Now you then finally acknowledge the other functional group, which is 2,5, 3-ethyl, 2,5-dimethyl, and of course finally the parent chain, which is 1, 2, 3, 4, 5, 6, hexane. So let me write it out here. 3-ethyl, 2,5-dimethyl, hexane. Very easy. All right. Now this is all the same. Don't be confused about its arrangements. All right, still the same thing, nothing weird here. You can see where the longest chain is. Pretty easy to spot out. These guys, these are organic compounds. They can undergo hybridization. So it doesn't matter the position you keep them, still all the same, represent the same structure. So this one is a little bent, but we know, we the smart ones, we know that is actually a very straight simple chain. So now let's acknowledge the root name first, of course, the root name and the functional groups present. So we will start by counting the carbon atoms. Carbon atom 1 2 3 4 5 6 7. Let's take another root and see 1 2 3 4 5 6 7. Okay, so at this point we have two chains with that, two equal chains. All right, so which one are we picking? So like I said earlier, the one with that has more functional group attached to it, the one that has more functional group attached to it. So if you look closely now, you see that it's actually this one that has the most functional groups attached to it. We have 1, we have 2, we have 3. Okay. Why the other one? Why this other one? Why this other one? We just have 1 and 2. This is a very special kind of, but we'll get to it. A very special kind of group there. We'll get to explain it, but let's just respect the rule first and name it accordingly. So we are taking this one. We're taking this guy here. So it's 1 2 3 4 5 6 7. Of course, this is not the correct numbering, but I just want to know the root name. So it's a heptane. Alright, so we acknowledge the functional groups there. We have 1, we have 2, 3. So naming it will be 1 2 3 4 5 6 7, the rest. So first of all, this is an ethyl group. Remember what I said, we acknowledge it first because of E comes before M. So it's going to be 3 ethyl. Please remember your hyphen. 3 ethyl 2 5 dimethyl heptane. All right. My writing might look very weird at this point, but I hope you just manage and hear you heard what I said. All right, it's 3 ethyl 2 5 dimethyl heptane. That's what I wrote there. All right, let's move on. Now we are, like I said earlier, we have special, special branchings. All right, we have the isopropyl branching, we have the tert butyl branching, we have the sec butyl, we also have the neo. All right, we have the neo, but neo, if you understand the concept of tert butyl, it's easy for you to understand neo. So that's why I didn't put it here. So let's get going and see how these weirdos are identified. All right, we have the first weirdo, but an easy weirdo. All right, let me just point this out. Whenever you see a branching that has a carbon atom that looks like a man spreading the legs, a man like this. I want to draw a man so you see. All right, that looks like somebody standing at his, right, spreading his arms and legs. It's an isopropyl. All right, that would be the prefix. All right, so let's go ahead and name this. Now we have seen. Okay. So we'll of course start by identifying the longest chain, which is 1 2 3 4 5 6 7. All right, let's not bother counting this. We know it won't be up to 7. So we know it's heptane. So from both sides, you can see it's located at an equal point. So if you count from 1, 2, 3, 4, it will all be the same. So what is the name of this compound going to be now? It's going to be 4-isopropyl heptane. Now, why is it called isopropyl? You might ask. It's not just a random name that is just given without any reason. Iso means equal. It means that on this carbon here, it has equally attached, carbon structures on its sides, and also there are 3. Iso means equal. Of that is of equal. Isopropyl, it has it's equal. It's an equal distance on both sides. Unlike the sec, we're actually going to get to that next. Sec doesn't have an equal distance attached to it. So what we mean is this carbon compound here, the first carbon compound that is out of there is evading this chain. All right. So this is 4-isopropyl heptane. This makes it 4, so it's 4-isopropyl heptane.